Hello everyone, in this second part of trigonometric integrals, we're going to check what happens when we are looking at other trigonometric functions that are different from sine and cosine. Combinations of secant, tangent, cosecant, cotangent that we can use on the same framework that we were using previously, the trigonometric integrals. So first, let's check what happens with powers of secant and tangent. And we can use a very similar strategy to what we did before with integrals of the form tangent to the m of x, secant to the n of x. The whole idea is, well, since the derivative of tangent is secant square, then we can separate some sort of secant square factor and compare the remaining even power that we're assuming of secant to an expression involving tangent using the identity secant square is equals 1 plus tangent square. Or notice that also, since the derivative of secant is secant by tangent, we can separate a secant by tangent factor and compare the remaining even power of the tangent to a secant. So let's see how that comes into play. So consider the integral tangent to the 6 of x multiplied by secant to the 4 of x. Here, what we're going to do is we're going to separate one secant square factor, and we can express the remaining secant square factor in terms of tangent. Of course, the substitution here is going to be u equals tangent, so that the du is going to be a secant square. Okay? So doing that, we have tangent to the 6 of x times secant to the 4 of x can be seen as tangent to the 6 times secant square of x times secant square of x. Now you can see here that if I make u equals tangent, I'm going to have the secant square x dx, so I'm going to have my du. So with that in mind, then let's convert the other secant square to 1 plus tangent square of x. And so now, if we make u equals tangent, we can have u to the 6 here times u plus 1 u squared times the u. And so this is going to become a simple power integration where we have u to the 6 plus u to the 8. This is basic antiderivative, so we have u to the 7 divided by 7 plus u to the 9 divided by 9 plus c. And then we can go back and replace this by the original variable u equals tangent, getting 1 over 7 tangent to the 7 of x plus 1 over 9 tangent to the 9 of x plus c. Okay. In general, the rule for this is that we can consider what happens if the power for secant is is even, and save the factor of secant square for the u's outside ones that we make u equals tangent. So in general, if we can have something of the shape tangent to the m of x times secant to the 2k of x, then notice that what we can do is we separate one secant square. And so once that we separate that secant square, we're going to be left with tangent to the m of x, secant squared to the x to the power of k minus 1. And then we transform that piece into 1 plus tangent square of x. And then we can do the substitution u equals tangent, which is exactly what we did in this example here. Okay? But that's pretty much the general rule for dealing with secant and tangent in this way. Now, if the power of the tangent is odd, we have the m equals 2x plus 1, then at that point we're going to save a factor of secant by tangent. Okay? And then we're going to use the transition tangent squared being secant squared minus 1. Why? Because in this case, the substitution is going to be different. We're going to be using the substitution u equals secant. Notice that here we have tangent to the 2k plus 1, and we have secant to the n of x, and so we can see this as tangent square power to the k, and we subtract one of this tangent, and we'll leave it here. We subtract one of the with secants, we leave it here, secant by tangent. So we have the derivative now of secant, which is secant by tangent. And so now we transform this tangent square into secant square minus 1, and then you can see the substitution. This is going to become u squared. This is going to become u to the n minus 1. and this secant by tangent here is going to be the du. For other cases, the guidelines is not as clear as we want to, and we might need to use different integration by parts or other identities and transformation to do different things in here. Sometimes we need to be able to integrate tangent by using the formula of integral of tangent being the logarithmic of secant. And if you remember where this is coming, this is because we have that tangent is sine over cosine, so we can make u equals cosine, that u will be sine, so we get a log of cos, and then we can transform that into terms of secants as well if needed, since cosine and secant are related. Now, another integral that is also useful for transformation between secant and tangent is going to be the integral of secant, which is going to be log of secant plus tangent. And if you don't remember how to do this one from calculus 1 in substitution, what happens with this is that you have secant and you multiply by secant plus tangent up and down. And once that you get this, then you get on the top secant squared plus secant by tangent, and on the bottom you get secant of x plus tangent of x. You, of course, are going to make a substitution where u is secant of x plus tangent of x. And so the derivative of that is, of course, the derivative of secant is secant by tangent, and the derivative of tangent is secant squared. So you can see that pretty much if u is the bottom, the u is going to be here, the top. And we get 1 over u du in the transformation, and that's just going to be log of absolute value of u plus c. And then we can go back to the original variable, and this is log of secant plus tangent. So sometimes we'll have to use that particular identity as well. So let's see one example of this kind of thing into play. Consider the integral of tangent cube of x dx. Notice that we only have a separation that we can do here, and it's a tangent of x by tangent square. And then we can transform maybe the tangent square and secant square minus 1, trying to look for somewhere where we can get the derivative. And so in that way, tangent cube can be transformed into tangent of x times secant square minus 1. And then we can separate this into integrals. This is tangent of x times secant square of x dx minus tangent of x. Now here we can use the integral that we discovered before, and similar here, if we do u equals tangent, the derivative is secant squared, so we can do this one by substitution, and this one with the integral that we just learned of logarithmic of cosine. Okay, or here we have log minus 1/2 of log of secant. Okay. So in the first integral, of course, remember that we did u equals tangent, so that the u is secant square. And this is going to be a constant on the manipulation of this type of integration. By the way, if you have doubts about the integration by tangent, there are a couple ways that you can get to that. Remember, tangent of x dx, this is sine of x over cosine of x dx. And so you can do u equals cosine of x, and the u is minus sine of x. Okay? And so because we have that, then we can say, well, minus the u really is sine of x dx. And so this transformation here is 1 over u times minus du. And this can be seen as minus log of absolute value of u plus c. And this minus, by property of the exponents, is just log of u to the minus 1 plus c. Now, because u is equals cosine, and so this is like cosine of x power to the minus 1. And so that's what gets me log of secant of x. But Of course, you can always consider also this as just minus log of absolute value of cosine. So it just depends of your convenience. If you're more happy with log of secant, then you can use this one. But if you want to use, of course, minus log of cosine, then you can also use that one as well. Now let's talk about using product identities. If depending on the trigonometric integral that you have, you might want to use trigonometric identities to simplify some of the different combinations that we have. We're going to have integrals from the type sine of mx times cosine of nx, or like sine of mx multiplied by another sine of a different angle to nx, or cosine of m times cosine of n. So two different angles is what happens. So some of the identities that we can use here are the multiplication or the product identities of trigonometry. So for example, sine of a times cosine of b is going to be 1/2 of sine of a minus b plus sine of a plus b. So if a and b are in terms of x, we're going to be able to do subtraction of these numbers. It is not going to be something that looks as bad as this. Sine of a, sine of b is the same thing. Is 1/2 of cosine of a minus b minus cosine of a plus b. And finally, c cosine of a times cosine of b is equals 1/2 of cosine of a minus b plus cosine of a plus b. So all these are combinations that we can use to simplify products. So let's see this in application. We have the integral of sine of 4x times cosine of 5x. And this integral can be evaluated using integration by parts, sure, but it's easier to use the identity that we checked before. Notice that this is sine of 4 times cosine of 5. So we can use this identity here. So this is like 1/2 of the subtraction between 4x minus 5x. So that's why you see minus x here. And 4x plus 5x, then you see sine of 9x. So if you have the identity available to you, or you remember the identity, then you can use this. Now notice that you can just pull out the minus here from the sign, and you get two single signs that are very simple to calculate by doing basic antiderivative or basic substitution. With here, the integral of minus sine of x plus sine 9x becomes 1/2 of cosine of x minus 1/9 cosine of 9x plus c. And so this is all that we can apply to simplified trigonometric integrals. Make sure to check more examples on the weekly practice videos.